Hey everyone, how are we doing today?
Hi.
Let's see. I've got lots of your projects graded, but I think some of you who are here don't have yours graded yet. So sorry, I am working on those things. So they are still slowly coming. I think I've got 5 more to grade, if I'm not mistaken. So I've gotten through a lot of them. Okay. Good. All right. What before we start other things, what questions do you have? I didn't get a chance to look at your DQs because I was busy grading the projects. So if you have a question on one of the DQs you turned in, I think a lot of the times you turn in DQs that you're pretty sure you got right. But if you have a question on one of the ones you turned in, feel free to ask, and I can open it up and take a look at it.
I had a question on mine, chapter 18, number 37.
Okay, shall I open yours up and see what you did, and go from there?
Um, so you want me to open it up in the?
No, I can open it up. I didn't know if you want me to open up what you posted and you want to do it that way.
Oh, yeah. So
Okay.
I labeled 1, 2, 3 kind of towards the end.
No, hold on. I'm not gonna have a clue what you're talking about until I actually look at it. Sorry.
Okay.
It's fresh in your mind. It's definitely not fresh in my mind.
Well, I also have it in front of me. So.
This is topic 6 DQ1. And actually,
Yes.
who's talking? Is it
Hugo.
Hugo or Hugo?
Yeah,
Okay.
Hugo.
Okay, so let me open up what you got here.
It was the an if and only if proof.
Okay,
And
show that an integral domain R satisfies the ascending chain condition if and only if every ideal is finitely generated. All right, good. Okay.
so
Here, let
I
me.
understood the forward facing. I did mine by contradiction, but
Okay.
I don't know if you see those little like 1, 2, 3s on the side there.
Here, hold on. I'm gonna share this and we can all look at it together. So I'll share the screen. Give me a second to move things around again. Okay, so first of all, do you want to remind so this is something we're going to talk about later today. So we can just look at this now. And what is the ascending chain condition? Just to make sure we understand what that is.
So it's basically let me. I don't really have 18. It's basically an increasing chain of ideals. So like the first ideal is, and I believe that's like a sub ring
So
of
yeah,
then and
yeah.
it continues
Mm-hmm.
not infinitely because it eventually ends because it has to have a finite length.
Okay, so that's the main point, right? So if I have an
Yeah.
ascending sequence, then it has to have a finite length, right? It has to stop. In other words, it can't be strictly ascending like that, right? So you can't have strict like strict supersets, right? It can't be getting strictly bigger for an
Hmm.
infinite amount of time, right? It's got to actually come to an end, and there's got to be a biggest one, right?
Yeah.
Okay. Okay, and we're going to use that for an important result today. So that's the definition. So ascending chain condition is the, and by the way, this is called a chain, and it's called ascending because it's increasing like this. Okay. And you're trying to show that the ascending chain condition is equivalent to, and what is the equivalent?
Uh, every ideal in the ring is finitely generated.
Okay, so every ideal is finitely generated. Someone's starting some construction noise right outside right now. So if you hear it and it bothers you, I'll close the window. Okay. Good. Okay, and so you have one of the directions. Is that right? You have this direction. Is
Yeah.
what you seem to be saying here.
Yeah.
Okay.
Yeah.
So
I understand that direction.
okay. Well, let's just make sure everyone does. So we have the ascending chain condition. and we want to show that every ideal is finitely generated. Hold on just a second. I gotta close this one. It's too loud, too much noise. It's like our class started and someone just started doing some noise outside. So yeah, so I have an so let's see. Let me not try to read what you did. You just tell me if what I'm doing is the same or something like it. So I have an ideal subset of the reals, right? And we want to show that it is finitely generated, right? So so I suppose what you did is something like this, right? So let A1 be an element of the ideal, right? And then look at A1, the principal ideal generated by A1, right? That's definitely a subset of the ideal. Okay. Is that everything? Well, if it's everything, you're done, right? Because then it's generated by one thing, right? And if it's not everything, well, so there's sort of like cases here, right? So case one, the principal ideal generated by A1 is I, and you're done because you just generated I with a single thing, right? So sort of case two is this isn't the case, so you're going to take some A2 in I minus A1, right? And you're going to look at the smallest ideal now containing both these things. We are using a little bit of the stuff we did last time, so A1 and A2 generated from both those things, right? And this will be the same as the ideal that I would get by just adding these together, right? So those turn out to be the same, okay? So I'm sort of doing a little bit of review of what we did last time too, right? So if I have J plus I, right?
Sitting in the car.
Sorry, what's that? Or
Sorry,
someone
I
was
didn't
just
realize my mic was on.
okay. Right. So the ideal, which is I plus J, would be the same as the smallest ideal containing I and J. So they'd be generated by these two things, right? Okay. And now you could say, well, same thing, right? If I is A1, A2, then you've generated it, right? And if not, so we'd be done in this case, right? If not, you'd have like a case 3. Now these cases aren't going to automatically in, right? Then you pick an A3. Okay, now what I'm doing here is a little bit informal, right? I'm just saying you keep doing this thing over and over and over, right? So it's a little bit on the informal side, right? But I think it's pretty clear this way. So I pick an A3, which is an I minus the two things we already have, right? And we keep going, and the claim is this has to stop, right?
Yeah.
Because otherwise we're getting this. We're getting A1 is a proper ideal in A1, A2, and that's a proper ideal in A1, A2, A3. And it would just keep going, right? Right? So it's got to stop. So eventually we reach some case N. Again, clearly there's something like an induction here that I'm sort of, right, there's a kind of a dot here. All right, so in some case N, A1 through AN, right, has got to give me the whole ideal, right? Otherwise, I would build an infinite chain, right? So that's kind of the formal thing would be, if after n steps you haven't built an infinite chain, you do it one more step. Either you build either you capture all of the ideal, or you can extend, right? And if you keep extending forever, you're using recursion, right, to keep getting the next thing, right? And if you can recursively keep getting a next thing infinitely often, right, then that would be a contradiction, right? So it's kind of an induction proof where you're defining something by recursion, and you would show that, if it were never finitely generated, then the recursion would never stop, right? There would always be something in there to grab, right? And that would give you a contradiction, right? So there's really an induction or recursion going on. Okay, so this is the direction you got, right?
Yes.
That's the direction we got. Okay. So now
way.
Okay, so now we want to go the other way. So now suppose I is finitely generated. I think you got the hard direction, by the way. Right. Suppose I is oh wait, I gotta be a little bit careful. So what do I really want to do? Let's be a little bit careful what I'm saying here. What is this doing? Oh, wait. Eraser. I want area. Right? Yeah, like that. Okay, so here I want to say something a little bit different. I want to say, suppose every ideal is finitely generated. I'm going to just write FG. Then ACC holds. Right. That's what we want to show, right? And this one I will also do by contradiction, right? So, suppose ACC doesn't hold. All right, then what does that give me? Well, it gives me a sequence of ideals. All right, that are increasing, infinitely long, right? Because that's what it means for this to fail to hold, right? So I get an infinite, strictly increasing set of ideals, right? Okay, now maybe here's a little bit of a trick. Is it true that if I have two ideals, here's a good true-false question, I and J, that I union J is an ideal? In general, would that be true? And again, maybe think about Z, right? Is it true that NZ union MZ is an ideal in general?
Yeah.
I heard a sound, but I'm not sure what that sound was. Was that a yes or no?
Yes.
Oh, so do you want to guess again? second guess. I mean, is the union is the union of those two things an ideal? I mean, by the way, one of the things we talked about last time is the fact that any ideal in Z, this is part of what we're talking about today too, has the form KZ, right? Because they're all principal, right? Or if you like, you could just call this K or something, right? So this is the saying is N union M, is that equal to some K necessarily, right? And that's just not true, right? I mean, this could be the set of all things that are multiples of 3 and the set of all things that are multiples of, I don't know, 2 or something like that, right? If I take the union of those things, I don't get something that is of the form, the set of things multiple of some K, right? You won't get that. Okay, you've got to generate from the union, right? Okay, but now the next question is, and this is like something we've seen before. Actually, you know what? Let me not erase. I know people don't want me to erase stuff. Let me I go back and not erase stuff. Okay, let me leave that. Let me just put, this is like a little aside, right? If I have an increasing sequence of ideals and I take the union, is that thing an ideal, right? And it can be, I'm just, let's just do an increasing countable sequence. So I have exactly the situation I'm in up there. I've got I1 contained in I2, contained in I3, right, etc. Going on forever, right? And now I'm looking at union. So I look at I equals union, I and the natural numbers of I sub I, right? So just taking the union of all those things. So usually if I just take the union of two ideals, they don't have to be an ideal, right? But this is a different setting. If I take the union of an increasing sequence of ideals, does it need to be an ideal? Is this an ideal? So what do you need to check? Oh, you got to turn on your volume.
If it's a subset of the other.
No, this is a union. So everything here is going to be a subset of this, right? I'm taking a union. So this is going to be way out here at the end, right? Bigger than all of those things, right? because we're putting all that stuff in there. But is that an ideal? Like, what do I need to check? I mean, this is good practice too for your tests coming up, right? To check that something's an ideal, what do I need to check? There's two or three things kind of depending on how you view it.
Does it have to have like the generator?
No. I'm not asking something specific to this question now. Now I'm asking something just completely general. All right.
Does it have to
if
be like non-empty?
Okay, being non-empty is part of it. So I was going to combine that with something else, but that's part of it. Hold on just a second. I'm going to save something real quick. Okay, I just wanted to capture that real quick. So I'm willing to give you that we did all of group theory already, right? So there's kind of a couple of ways of saying so. Someone give me one good definition of saying I subset of R is an ideal. What do you need to check?
Closed under multiplication.
Okay.
I is an.
Go ahead. Yeah, can we say that in a more simple form? Maybe not simple, but more sort of compact form. Go ahead, Philip. What were you going to say?
Oh.
Or whoever's going to say. Go ahead.
Yeah, I think we need to check that I is a non-empty additive subgroup of R.
Okay, so this is one of the things. Yeah, so you want to show that I, together with its plus and zero, is a subgroup, right, of R with its plus and zero. Right? Okay. And then being closed under multiplication isn't enough for what we need next. What do we need next?
Like that is commutative, like RA and AR have to.
Nope. Commutative has nothing to do with being an ideal. I mean, it does in some sense.
Is it like left coset and right coset?
Someone say it. This
Did
is what
someone already say that
minus
it absorbs multiplication from the ring?
Closed under multiplication from the ring, right? So Ri needs to be contained in I, and IR needs to be contained in I. Now, if it happens to be commutative, right, then those two things say the same thing. So we could just check one of those things, right? But the ideal needs to be closed under arbitrary multiplication from the ring. Remember, again, when you're forming this R mod I thing, right, this thing is becoming the zero of that structure, right? So what this thing is sort of saying is, you know, anything times zero is zero. That's sort of how this is being interpreted when you look at that quotient structure, right? So these are sort of this is kind of a quick way of saying what I wanted to say, right? Now, being a subgroup does have a bunch of stuff to it, right? It needs to be non-empty and it needs to be closed under addition and all that stuff, right? So now we need to check that subgroupness, right? So you know, if I take A and B, you know, in this I, right? Is it true that A plus B is an element of I and that A minus B is an element of I? Right? So, you know, question mark, is that true? Remember, I have this increasing sequence of ideals and I'm taking the union and getting I.
Yes, that's true.
Okay, so it's true. And why is that? Because A has to come from somewhere, right? A has to come from some I, right? And B has to come from somewhere. B has to come from some IK, right? And if I let J equal the max of I and of little I and K, right? Then we have that A and B are in IJ, right? Okay, but this is an ideal. So this is closed under addition and subtraction, right? So it's definitely the case that A plus B is in I, because A plus B is in IJ, right? And A minus B is also in IJ, right? Now, in order for this to work, I need to be able to go to this max and take that bigger thing, right? So that's the reason these need to be ordered like this, right? Again, if they're not ordered like this, right, then what I'm trying to prove here is false, right? And what about this other condition, that R times I, right? So the other thing I need to check is that if A is an I, right? Remember, this is just the union. Then RA is an I. Let's go ahead and assume commutative. Remember, for in class, we're going to assume we have commutativity and we have unit, right? So we don't have to worry about those two things. Okay, and so same kind of argument, right? If A is an I, where does it have to come from? This is the union of all those things. So where does A have to come from?
And I.
Yeah, it's got to come from one of these, right? So, for some I, right? But this is an ideal, right? So RA is also an element of I, right? But that means that RA is an element of I, right? Because everything in here is contained in I, right? So the point is, whenever you grab something, some finite number of elements from this increasing union, all of those occur somewhere along the way, right? And so you get to use the closure properties of that sort of intermediate place to get the closure properties for everything else, right? Does that make sense? So if I were trying to add together an infinite set of elements from I, that would be a problem, right? I might be grabbing things all the way along the way, right? But we're never doing any sort of infinite algebraic operations, right? We're just doing finite sums and stuff. Okay, so we're sort of staying. So again, I mean, just in terms of pictures, right? If you think about these as sort of getting bigger like this, right? So I have I0 and I've got a bigger I1 and a bigger I2, and it's sort of going out, and I'm taking the union as this whole I, right? Then whenever I take an A and B from in here somewhere, and B, right, it gets caught by one of these things, right? So it ends up being in some IK, right? And then I'm just using the fact that I have these closure properties for that IK to get the closure I need, right? Because those closure properties only involve finitely many things, right? So we are using the difference between finite and infinite here. It's sort of an important thing going on, right? So now what I have is I have the union as this I. Now you got to remember what we were doing. We're trying to show way back here somewhere that let's see. Sorry, where did I see it? Oh yeah. So yeah, I'm supposing every ideal is finitely generated, right? And towards a contradiction, right? I'm saying suppose we have this infinite sequence, right? Now we've built an ideal. Okay. Now our assumption is that every ideal is finitely generated, right? That's our assumption for this part of the proof, right? So what do I know about this I? Is I know it is generated by some finite number of things, right? Okay. But where do these things come from? Right? So like AI will come from some AJI, right? And then I can just take K to be the max of all those, JIs for I going from 1 to N. And again, it's sort of like all those things are coming from somewhere along here. So I just take a big enough one to grab all of them, right? It's only finitely many, so I can do that, right? And so I get that this generating set, so I get A1 through AN is actually in some IJ, IK is what I called it here, right? Okay, but what does that tell me? It tells me that A1, the ideal generated by those things, is also contained in IK, right? But this was supposed to generate all of I, right? So this IK has to already be everything, right? So there was not a strictly, we get a contradiction, right? There's not a strictly increasing sequence of ideals, right? So if we have the ascending chain condition, we get that every ideal is finitely generated. If we have every ideal is finitely generated, we have the ascending chain condition, right? So we have those two things. Does that make sense? Is that good, Hugo? You got it?
Yeah, I got that. I just because I got stuck on it. So I looked at your solution to it, and I guess that's the one that I was having like trouble understanding. The like, I don't know if you see the little 1, 2, 3s kind of on the left, where it says like choose an end such that AI is an element of IN, and then that second line and that third line, like those last 3 lines, I got from
mean, I'm
your
doing
solution. I just didn't understand like how those followed logically. I was just
I mean,
having trouble
I think
understanding
I'm
that.
doing just exactly what I did here, right? I think I'm proving this thing here. So, you know, the union of AI is, sorry, the II is equal to this finite. No, it's exactly the same thing I just did here, right? So, you know, I'm saying the first line here is that, right? That's this part here, right? And then I'm saying go along and find an ideal that contains each one of the generators, right? And then I'm just saying take a a sufficiently large K that picks up all of these things, right? Because they're an increasing sequence. If I take a K just bigger than all of these JIs, right, then all of these generators are in that, right? That's that's essentially what I'm doing here. I'm picking an N, right, large enough so that all those things are in there, right? But then what you have is you have that this IN. So in these notes, right, I'm calling N instead of K, then IN is equal to I. I mean, maybe I wasn't doing it by contradiction, right? You don't have to do it by contradiction, right? I mean, so the one bit of difference might be this. I might have just been saying, suppose you have an increasing sequence, and I'm not assuming that it's strictly increasing, right? Right. So suppose we have that, right? So now I'm not doing it by contradiction. I'm just going to directly get that this sequence has to stop, right? It's got to stop growing at some point. All right. So now, but the argument's still the same. I define this to be the union of all the IIs, right? And then I use the fact that this is finitely generated, like that, right? And so I pick something large enough to pick up all these generators, right? So, you know, A1 through AN is in some. I don't want to use N again, so let me say I'll just call it K again, like I did a minute ago, right? Those are all in there, right? But since this is everything, right, it's got to be that this is just the biggest ideal there is, right? So all the rest of these just become equalities because this already contains everything, right? So now that's not proving it by contradiction, right? So I'm not assuming there's a strictly increasing sequence. I'm just showing that every increasing sequence eventually has to stop getting bigger, right? So it's a slightly different argument, right? Good. Okay. Well, that's good. That's part of the argument. Part of the stuff we need to do today, anyway. So, any other questions? Chances are anything you ask will relate to stuff we're doing today. Nope. We're good for now.
I was wondering if there is some, I don't know, I don't want to say algorithm, but some way to look at splitting fields in various things that kind of, I guess, understand what's going on there.
Okay, so I got to think about the order I want to do things in. Well, let me answer that question partially, because this now you're jumping sort of way ahead from where we are now. But it is today's topic. And by the way, I mean, we can talk more about this next week too, although next week we're going to have like the in-class part of the exam. So next week's our exam week again, right? So we're going to be back to doing that. Well, let me talk about it, because that's sort of, where we're going anyway. And this is an important, how do I want to do this? Let me say some things. So everything is in the notes, and let me sketch out the important things without proofs. All right. Just so we sort of step through things, and then let me get to your question and kind of address what we can do to see what a splitting field looks like. Okay. Does that sound good? So let me do something here along the way, right? So there's all this stuff about ideals and UFDs and PIDs and all these things, right? So let me just sort of briefly sketch through that bit of stuff, okay? So we just did something with the ascending chain condition, right? What is a PID? I mean, hopefully you've read the definition and sort of looked at this. So what's a PID?
Principal ideal domain
So what does it mean though? So I've got
is
R
a
as a
special type of
PID.
integral domain where every ideal can be generated by a single element. For example, the integer z's form a PID.
So for any, whoops, I subset of R, right? There's some, R and I, right? Such that I is just generated by R, right? And so, another way of writing that is that I equals, again, I'm assuming commutativity right here, right? So I is just equal to R times R. Maybe R is bad. Let me call it S. Right. So I can find something in the ideal so that the whole ideal is like that. Okay. And right, your sort of first example of this is Z. Z is a PID. Whoop, not a pip, a PID. PID. Now we're also, I mean, part of what we're saying here is that this is a integral domain, right? So that's what the ID part is saying, right? Okay. So we want to be a little bit careful because we could be in a case where we have all principal ideals and it's not an integral domain, right? I mean, that's also possible, right? So that doesn't have a specific name, right? But it's something that we could look at, right? I mean, so you might have a non-integral domain and try to show that all the ideals are principal, right? So the integral domain part might fail, right? Even when you have commutativity in unit, right? You might have zero divisors, right? And still have something where all the ideals are principal, but it's not a PID, right? Because it's not an integral domain, right? So just keep that in mind. So, but we are mainly interested in integral domains where all the ideals are principal, right? And Z is sort of the base main case for that. Now we just looked at ACC is equivalent to all ideals are finitely generated. All right. So what is the relationship between PID, all ideals are principal, and ACC? All right. What do I know about a ring where all the ideals are principal? Like, okay, if I have a ring where with the ascending chain condition, do I necessarily have a principal ideal? All right, because this was
Yes.
equivalent to being finitely generated. So is it true that if I'm finitely generated, I mean, what is another way of saying principal? I'm generated by one thing, right? I'm generated by a single element, right?
So I might be wrong, but I was wanting to say that the PID basically means like it also like satisfies the ACC, like it will be an ACC if it's a PID.
This is definitely true, right? Because this says everything is generated, generated by a single element, every ideal, right? So definitely if every ideal is generated by a single element, they're definitely all finitely generated, right? It's not true the other way around, right? I mean, if something's generated by two elements, it doesn't need to be generated by one element, right? So I mean, that isn't the case. I mean, you can take examples like in ZX, right? You can take the ideal with 2 and x, for example, right? So this is generated by two things. So ZX does satisfy the ACC, but it is not a PID. I mean, it's a good example to keep in mind for a non-PID, right? Actually, okay. So it does satisfy the ascending chain condition. I think we're not going to actually prove that, right? So I mean, the theorem there, it is in my notes. It is that if R is ACC, then Rx is ACC. Okay, I think it's like one of the last things in my notes, right? So that's actually true. It's not true, right? If R is PID, I mean, maybe it's just worth writing this down. Then Rx is PID. These are good true false questions. This is not true in general, right? And a good example is just ZX, right? And there's an ideal right there, right? Which is generated by two things and not generated by one thing, right? Now I'll leave that for you to think about, but that's the case. Okay. All right, so PID is going to imply ACC, so that's good to know, right? Now, how did we get PID and Z? So how did we show? We did this last week, but toward the end. Z is a PID.
There's no remainder.
It's not that there's no remainder, but we use the remainder, right? We use the Euclidean division algorithm. Whoops. Oh, my hands. Euclidean division. Okay, and I'll just remind you, right? What we do is you take I contained in Z and ideal, right? And you simply look at the set of all A and I. These are integers, right? Such that A is greater than 0. Right? So this is some set. Okay, so if it's the 0 ideal, there's nothing in there, right? So that, but the 0 ideal is principal, right? Because it's generated by 0, but it just has 0 and nothing else, right? So that's all it has in it. But if it's a non-zero ideal, then definitely this is non-empty, right? There's got to be some integer in there, right? Maybe it's got -2 in there, right? But if it's got -2 in there, then it's got to have 2 in there, right? Because it's got to be closed under additive inverses, right? So there's definitely going to be something in here, right? Given that there's something in here, right, you can define, let's say, S to be the minimum. Okay, we're going to do the same proof in general in just a minute, but for Z, this is what we do, right? Why is there a minimum here? That is, I've got a non, I mean, what is S? S is a, so it's a non-empty subset of the natural numbers.
Is that just the well ordering principle?
That's right. Yep. So min S exists. There's something in there. And this, yeah, that's exactly right. It's the well ordering. So we are using that. We use it quite a bit in this class. Right. And then the argument was, so the argument was then pretty simple. So the claim now is that I is generated by this S, right? So that's the claim. So you take some A, which is an I. Suppose, well, I guess I don't need to suppose any. Let me just do it direct. Let me not do a suppose something. So then A is equal to QS plus R, right? And what do we know about this R is that 0 is less than or equal to R is less than S. I mean, that's part of the way the Euclidean division algorithm works, right? Okay. But this thing is an I, and this thing is an I, right? So we can subtract and we get A minus Q S, sorry, this should be an S, is equal to R, right? So this thing is an I, right? But S was the smallest thing in I. It's not 0, right? So the only option is here, this has to be 0. Yep. And if this is 0, then what we're actually proving here is A equals QS, and that means that A is in S. But A was just an arbitrary thing in I, right? So that means that I is contained in S, right?
So Doc, how was I wrong when I said that there was no remainder? Or was that just too simple to say it like that?
Yeah, it's too simple. We need to say we're going to choose the element of I with that's the least positive element of I. No, that's what you need. You need to say we're going to choose the least positive element of I. That's going to be our generator S, and then we have to prove that generates the ideal, right? So, I mean, in the end, we show that when we divide by that s, the remainder is 0, right? But we need that s first, right? We need to say what the generator is, right? Good. Now, if I could
to say the generator.
If I could duplicate that sort of process, right? Then we could show other things are principal ideals, right? And hence they would have the ascending chain condition, right? So they'd have all those nice properties. And so the trick here is so when we have an R, so here's the next thing, which isn't quite a principal ideal, which isn't quite, how do I want to say this? Isn't quite Z, but will prove that R is a principal ideal. So R is a Euclidean domain. Whoops, sorry. If there is, a map F going from R to the natural numbers, all right, such that for all, let's say S and let's say, okay, R and like R, I want to use R for remainder. So let's say S and T and R. All right. There is a Q and R in R such that F of, such that, so two things, such that T equals QS plus R, right? So that looks like we're dividing by S and getting T, right? And secondly, I want to know that F of R is strictly less than F of S, right? So for every S and T we have in there, we can sort of take T and write it out, kind of where we've divided by S, so to speak, right? And the function F is decreasing on that, okay? So let's think of an example. And by the way, I'm not saying these are unique in this case, right? So that I'm not saying. I'm just saying that I have this function, right? And that's all I need. So let's see. So first of all, let's see that this does it, right? So if R is Euclidean, then R is PID. Okay, and the proof is exactly the same, right? So I take I contained in R, right? Okay, what am I going to look at? What element am I? So I want to show that, so let me just say this, want I is equal to S for some S, right? Okay, what S am I going to choose? Let S equal what?
Sorry, say that again, Professor, because my system just froze.
So a minute ago, we proved that every ideal in Z was principal, right? And the idea is I took an ideal in Z and I just took the smallest positive member of the ideal, right? And showed
So
that
A?
generated the ideal. So
make A an element I.
So I want to pick some S in I with what property? And it's got to involve that Euclidean function F, right?
But didn't you just say it's going to follow the exact same pattern the other proof we just did?
It's going to follow exactly the same pattern, yeah.
So wouldn't that be A?
I don't know what A is. What is A?
It's an element of I or R. I.
Okay, again,
A is greater.
so let me review the other one again. We took an I, that's an arbitrary I, right? And we fixed a specific element from I, namely the unique thing which is positive and smallest, right? So we picked a specific thing, right? So now I've got I subset of R. I need to pick a specific thing in I, which is going to generate the rest of I, given the fact that I have this function here. But it is, otherwise it is exactly the same. I mean, but there I picked the specific thing to have a minimum positive value in I, right? That was the way I picked it. So I've got an F. This F is going into the integers, not into the integers, but into Z, right? I mean, into N, right? Into the positive integers, right?
Oh, so this is connected to that stuff above the line. Okay, my
So
bad.
is S1 here?
The
There's no one.
generator for that would be T, wouldn't it?
No.
If you're putting S on the outside, because
There's no
R is
T
always
here.
the remainder.
The
Are
only
we
thing
connecting this to the part
only
that's
thing the only thing we have right here is I subset of R. I need to pick an element out of I that's going to generate I, right? That's all I've got. And I've got my F. I've got this function F, right? F is a function from R to the natural numbers with this property here.
Is R an element of R? Like lowercase r is an element of R?
I'm not sure what R, well, what is R? What R are you choosing?
Like, so I have in my notes like ideal equals S equals like R1, S1 plus R2, S2, and then Ri is an element of R, Si
Okay,
is
so
an element of S.
so stop. I want to duplicate exactly the argument we did above. I need to pick a single element of I, right? Okay, in this case, using F, right? Which is going to generate the rest of the ideal, and the argument's going to be exactly the same as it was above. So there was none of that stuff in that argument above, right?
Can we say S should be equal to the GCD of all the elements in I?
Well, there's no GCDs here, but these are mapping into the natural numbers, right? So I can just take, so I'll just say it. I take S to be the n element. So I can't say the because it's not unique anymore, but any element of I with f of s, whoops, positive, again, just like we did with the integers, right? Positive and as small as possible. So this is exactly what we did for the integers, right? So you know, if I look at S to be the set of all f of s for s and I, such that f of s does not equal 0, right? So I want to avoid the 0, right? So I'm just looking at this set. Well, this is a non-empty subset of the natural numbers, right? So it's got a minimal element, right? So it has a minimal value for this thing. Now, maybe lots of s's are mapped to that minimal value. We aren't ruling that out, right? But there is a minimal value here for that thing, right? And now the claim is going to be for any such s, right? So I just picked anything with as small as possible value as I could that's not 0, right? Then my ideal equals s, right? That's the idea. Right? And the proof is exactly the same, right? So take A, which is in I, right? Now, what did my F let me do? Let me write A down as some sort of product like that involving S, right? So A equals QS. In other words, you're kind of dividing by S, right? Plus R, right? And the property that I have here is that F of R is less than F of S, right? But again, that is in I. This is in I, right? So R is A minus QS, right, is in I, right? And its value on F is less than that of S, right? So the only possible value is 0, right? Because if it were something smaller, we would have chosen that for S instead, right? So this thing has that value 0. Okay, right? So we're getting here that A equals QS plus R where f of r equals 0, right? Let's see, I guess I need one more fact about my little function here is that I think this is for free, but I'll just add it to it, is that f of r equals 0 implies r equals 0. Right? Because I either I need to prove that or I need to add it, so I'll just add it for now. Okay. So assuming that this gives me that r equals 0, then I have that a equals qs, and we're done, right? And we're done. Because then what I have is I have that A is an element of S, but A was an arbitrary element of I, so I have that I is contained in S, right? Clearly the other direction is true, right? So that S has to equal I, right? So just to make it more clear, if Z is R, what is my Euclidean function? What Euclidean function am I using that has the property that for any t and s and z, right, I can write t equals qs plus r, where f of r is less than f of s.
You're asking us what should you be writing next, or you just gave it to us?
No, I'm just saying, I mean, we proved it for Z, and when we proved it for Z, I did sort of implicitly use some Euclidean function. We just proved it above for an arbitrary Euclidean domain, right? And I'm saying, what is the Euclidean function for Z, right? What is the actual Euclidean function we're using here for Z?
I guess I'm confused, Doc, because on my notes, when I was looking up and just trying out my definition for the Euclidean function, I have something where it says D, open parentheses, A, close parentheses, equal the absolute value of A, is the division of the algorithm and how it works. And I don't see any of that notation in your notation, so I guess I looked at the wrong type of notation.
Yeah,
And I know that the size, I know that the absolute value is talking about the size, but I thought that it was saying that D is what we're dividing by, because it says the division, it starts off talking about the division of the remainder. So I guess I am disconnected from what you just wrote because the notes that I took don't connect to what I
it's the
see
same
up there.
thing. Okay, I mean, I may be changing variables, but I have an S and a T, and I'm saying that we can take T and divide it by S, right, and write it like this. This is just the
I
Euclidean
understand
division
all of
algorithm.
that. I guess that's, so the result is actually the Euclidean, isn't that result?
No, this is just the plain Euclidean algorithm, right? There's no GCD here. There's none of that stuff, right? This is just the basic Euclidean algorithm. This is just division. This is division with remainder, right? For the integer.
So does result similar? Is it similar to Euclidean division then? Or they follow the same kind of model?
It's a more general. I mean, it's computing something else, but you use this to prove Biz out, right? That's what we did that way back in the first week, right? I mean, you use this to prove Bezo's theorem, right? So sometimes it's called the generalized Euclidean algorithm or something like that. But I mean, you did say along in that discussion, you did say what the right function is. So can anyone either recall what she said or guess what the right function is here for the integers? It's sort of an obvious one once you see it, and it's one you're very familiar with.
Is it just one?
No, everything does not have remainder 1, right? I need this to be true.
Oh, then 0.
No, everything does not have remainder 0, right? I can divide integers by other integers and get other remainders, right? The question is, what is I need something to be decreasing. I'm doing a division, right? I need something to be decreasing between S and R, right? Usually, I mean, one of the restrictions for the Euclidean algorithm is 0 is less than or equal to R is less than S, right? And we're usually assuming that S is greater than or equal to 0, right? So suppose I drop this restriction and I need this anyway. What is another way of doing that? Instead of having S, I might have absolute value of S, right? And instead of having R, I might have absolute value of R, right? And then I'm getting the same thing, but I'm just putting absolute values in there, right? So the Euclidean function from Z to N is just f of n is the absolute value of n. That's the Euclidean function, right? And then what the Euclidean algorithm says is, given, the old Euclidean algorithm from Euclid, right? Given A and B and Z, there exists a Q and R such that, right, B is equal to Q A plus R, and the absolute value of R is less than the absolute value of A, right? So I could just say it like that, where we have absolute values. But that's equivalent to what we've been saying. And so I'm not putting any restrictions on R being greater than or equal to 0, or A being greater than or equal to 0. I'm just taking arbitrary integers and say, do it this way, where I throw those absolute values in there, right? So the sort of hidden Euclidean function that we've been using all along with Z is the absolute value function. That's the one we're using, right? Okay. We're aiming at, well, lots of things, but one of the things we're aiming at is sort of looking at polynomials over fields, right? So what did you learn about polynomials over fields and Euclidean division? And also you teach this in high school, so you all know it.
It's the irreducibility.
No, I'm not. You don't teach irreducibility to kids in high school, but you do teach
No, we
them how
teach
to
them the
divide.
factor, and we use the binomial theorem, and we know that when you get to a point to where you can't factor.
Okay, but right now we're talking about division, right? And we do teach division, long division of polynomials, right?
Synthetic division and factoring.
Not synthetic division, long division of polynomials, right? So I have f of x and g of x, right? In some, let me just say r of x. Let's see where we actually need something here, right? Let's see where we need to be in a field here, right? And then the claim is that I can find there are some q of x and r of x such that g of x, so I'm going to divide by f of x, is equal to qx rx, not rx, fx plus rx. So that, again, this is supposed to be the remainder, right? And when we're doing this sort of division of polynomials, what is the property I want Rx to have relative to Fx, right? So these are the two things that enter into the Euclidean function stuff, right? So when do I stop
we want the Rx to be less than f of x, because if you're saying f of x is the generator, then we need it to be 0 is less than r of x, which is less than f of x.
So what about Rx do we want to be less than Fx? Again, when you're teaching how to divide, like if I divide x squared plus 3 over x plus 2, right? When do you stop?
When the degree is...
When the degree is no longer, yeah.
Yeah, we want the degree of Rx to be less than the degree of Fx. That's what we need, right? Okay, so can you guess what the Euclidean function is? Oops. That we're going to try to use.
I'm trying to catch up with writing my notes. Oh, we're going to use that z divided by.
Remember, I want a function from Rx into n, right?
Use a mod, something.
And we know that when we teach this to kids, we are looking for that, right? So isn't there an obvious function sitting there, which is going from the polynomials to the integers to the natural numbers?
Oh, is it derivatives?
Complex numbers, complex roots.
What is written right here? Everyone write what's written right there. I mean, what are we're doing? We're doing division, right?
He said
And we're,
degree of R of X is, I can't really read that, boss.
but
I'm just gonna
but it
be
says
honest.
degree of Rx is less than degree of Fx.
Right, okay.
I mean, you guys told me that, so that's what we got there, right? Doesn't that look like the condition we need for the Euclidean function? Don't we need something to
Yes.
be decreasing when we divide?
Yes.
Okay, so what would a natural guess at what the Euclidean function is? Is the output of
F
this an
of
integer?
X, the degree of F of X, no, the degree of R of X has to be less than the degree of F of X?
That's
Oh, you
when
already
we
wrote that.
that's when
You
we
just wrote
stop
that.
dividing. Yeah, I'm just asking when we're looking at polynomials over R, given what we're looking at here, what is a natural suggestion for the Euclidean function, for the thing that's supposed to be mapping from Rx to n and decreasing when we divide like this? And if you look at this right here, right, it's telling you exactly what to say.
Would it be the degree of f of x is equal to the degree of r of x?
This is just the degree of, right? Degree of, yeah, f of x. It doesn't matter what f and r. These are just arbitrary things, right? So, for f of x in Rx, for any polynomial at all, right?
The degree of
The function is the degree function. That's the Euclidean function here, right? And we just, and if our division algorithm's working, it does what we want it to do, right? Because when I do the division, I stop when the degree of the remainder is strictly less than the degree of the thing I'm dividing by, right? And that works, right? That works. You've done it many, many times, right? What do we need? So why do we need, can I do this in an arbitrary ring? I mean, can I do this over ZX, for example? Like, can I take 3x cubed plus 4x minus 5 and divide by 2x squared plus 3x plus 2? Can I do that? Where all the
No.
coefficients have to stay in z, right? Yeah, no, right? Because if you're going to do it, say you're going to do it over the reals, right? Then what I have here is like this. I have like 3x cubed plus 4x minus 5, right? And over here I've got my 2x squared plus 3x plus 2, right? And then what I need to do is like try to get rid of that thing right there, right? So I would try to multiply this by 3 over 2, right? I try to multiply this by like minus 3 over 2x, right? In order to make, so then this would become minus 3x cubed, and I would cancel out that term and we keep going, right? But this is invalid now because that's not in z, right? So we've sort of left our ring, right? We've gone out of our ring, right? But all I need to do this is I need to be able to divide, right? Should be sort of clear that if I can divide, I can do this process over any ring at all, right? As long as I can divide, I can divide polynomials, right? Does that make sense?
So what you're saying is the leading coefficient must be divisible by the leading coefficient of the divisor.
Yeah, but the leading coefficients can be anything. So what I'm really saying is that you can't just have a ring here. You need a field, right? You need to be able to divide, right? So if we want to have a Euclidean function, we can't be looking at. And by the way, a minute ago, I said the ZX is not a PID. I mean, and I gave you an example, right? So if it had a Euclidean function, it would be a PID, right? We'd have a contradiction, right? So that can't happen anyway. But if I take a field f and I look at fx for f of field, then we have the Euclidean division over them. So it's so fx for f of field, are very similar to z, not to zx, but to z, right? So they're both rings, right? So this doesn't have inverses, right? So this is itself not a field, just like Z is not a field, right? But it does have the Euclidean division algorithm over here, right? So if I take any two things in a field, right, I can, if I take an fx and a gx in a field, over a field, then I can, in fact, do this thing where I get gx gx equals qx fx plus rx. And by the way, I'm assuming that we have commutativity in unit. Otherwise, all the stuff we're doing with, polynomials and stuff gets confusing, right? Because we're assuming multiplication by polynomials and stuff all behaves like we're expecting it to. Synthetic division does work also, right? But this is more general. This is just taking any two arbitrary polynomials and doing a division, right? Okay, so so the Euclidean function here is just degree of fx, right? This is a map, right? So this is fx getting mapped to degree of fx, right? That's a map from fx to the natural numbers, right? So that's my Euclidean map. Okay.
Slow down just a second, please. I'm still writing. And could you repeat? You said f of x maps onto the degree of f of x. So
that's the Euclidean function. That is the Euclidean function we're using. Yeah.
Okay. And is that onto if it's just
yeah, I mean, you can
x?
I mean, you can find polynomials of any degree, right? I mean, it's onto just because I can map xn gets mapped to n, right?
Right. But wait, would we need to know that for this or no?
No, I mean, so if I call this function, let me call it e for Euclidean function, right? Again, what you need to know is you need to know that e going from fx to n. So for this specific setting, right, we need to know that's our function, right? So that's the degree.
What's
function.
That in between the e and the f?
Just a colon. It's a function notation.
Oh, okay, my bad.
Right?
I was just,
this is the Euclidean function, right? And the properties we needed to have is that so I'll just write it out again. So for f and g and fx, there is, I'm leaving off the of x part because it doesn't really matter, q and r in fx, such that g equals q f plus r, and the property is that e of r is less than e of f. Right? This is the sort of important, descending like Euclidean property. Right. So we need this kind of, quotient with remainder formula, right? And we need that this function e is descending there, right? That's the general definition of a Euclidean function. So in this particular case, right, e of f is just the degree of f. That's what we're using for the e of f. Okay. Another example that's good to remember is the Gaussian integers, right? And so they have a kind of division as well, because you can divide in the complex numbers, right? So if I take a plus bi and I divide, right, by c plus di. Now in this case, I'm thinking about a, b, c, and d are all integers, right? So the result I get here will not be an integer generally, right? And if you work it out, what do? You multiply by this thing.
Conjugate, yeah.
And you get some sort of complicated thing, which is going to be what, ac plus bd over c squared plus d squared plus I times AD let's see, it's actually BC minus AD. So BC minus AD over c squared plus d squared. Okay, that's an I, right? So you get this complex number. Now this is generally not an integer, right? But what you can do is you can say, let's round those two things, right? So I'm going to take q of x to be the rounding. Geez, round. Okay, of ac plus bd over c squared plus d squared plus I, and then round. So here we definitely are losing uniqueness, and then bc minus ad over c squared plus d squared. Right. So sorry. I mean, that's the same as that there, and that's the same as that there, right? So I'm rounding it. So now these are in z, right? I'm just rounding. Right. So if you think about z as the grid in the complex plane, right? So we're taking some number that's maybe there, and we're rounding it, right, to the closest grid point, right? Is more or less what's happening, right? And then the remainder will just be my original function. Oh, sorry, will be sorry, not x. The remainder, r, will be the thing I'm dividing. So a plus bi. No, the thing I'm dividing. Sorry, I got to get this right. It'll be a plus bi minus what is it? It's oh yeah, this thing here. So whatever, and I don't know why I called this qi. This is just q. Dang it, q. So this is now some e plus fi, right? So it'll be this thing c plus di. Okay, so something like that, right? And so this now is a complex number, right? This is the thing we're dividing by, right? This is the thing we're dividing. This is the remainder, right? So writing this another way is I have a plus bi, the thing I am dividing, right, is equal to c plus di, e plus fi, plus this remainder here, plus r, right? And it turns out that what we can use for r in this case is basically the magnitude of r squared, right, is what we can use for. So in general, right, so the map that we're using here, so this is our Euclidean map, right, there, is going to be that thing there, right? So it's going to take an a plus bi, and it's going to map it to a squared plus b squared. So the magnitude squared, right, of that number. Okay. So if I drop all the ai's, et cetera, if I just take a xi and a theta, right, in zi, right? So just use these as like notations for complex numbers, right? Then I can divide, right? And I can get xi is equal to some eta theta plus r, right? And so I'm dividing by this theta. That's what I'm doing up there, right? And what happens here is that the magnitude of theta squared is actually less than 1 over 2 the magnitude of r squared. So it's decreasing like that. Hold on just a second.
So no matter what type of division we're doing, we're going to always have at the end this relationship that you're showing where something's less than something, because you've done 3 different types, and that box that you put just there is that theta squared?
Yeah. So here our Euclidean function is just mapping xi to xi squared, right? That's the map that we're using there. And this is just the magnitude of the thing squared, right? Right. So I mean, it's not true everywhere. I mean, the point is, I mean, what we have is we have z fx for a field, zi for the Gaussian integers, right? These are all Euclidean domains. They all have a kind of.
That's why they all follow the same pattern, because they're all Euclidean domains. Okay.
Well,
so would those be subsets of Euclidean domains? Just curious.
Sorry, say it again.
would those be subsets if the group of Euclidean domains, those would be subsets of Euclidean domains?
I'm not sure exactly. I mean, these are Euclidean domains, right? Each of these things is a Euclidean domain, right?
But they're cosets, they're not the same type, right?
No, this is the
No,
ring
never
of
mind
all
that. I'm
polynomials
just
over fractions.
I'm just trying to make some connection to some vocabulary using something else. That's okay.
I mean, this is just like when we add any root to something. This is the set of all a plus bi, where a and b are in Z, right?
Yeah, I
It's
got
not
that.
it's not a field, but it is a Euclidean domain. So it is a PID, for example, right? Okay, so keep that in mind. We also showed that every Euclidean domain is a PID. Okay. Let's see, I'm not going to be able to do everything that's in the notes. Again, all of this is in that one set of notes I said we were going to be using for the last few weeks, right? But this is important, right? So it's important to understand how those things are become Euclidean domains, because really the proof is always the same. You need to find some function which is behaving like a Euclidean function, and then you get that it's a Euclidean domain, right?
In your
fact that
notes, you said, Dr. K, in your notes, you said there's a very important order in which those go that could be a test question. Did you just present it to us as the order in which we would need to know it on a test question?
No, I want you to know true things, and it is true that Euclidean domains are PID domains, or are PIDs, right?
I get
It's
that, but
definitely not the case that PIDs are all Euclidean domains, right? So there's a true-false question, right? Is it true that every Euclidean domain is a PID? Yes. Is it true that every PID is a Euclidean domain? No, right? There's all sorts of potential true-false questions here.
No, I understand that, but I'm asking a very specific question because in your notes you did exactly what you just said there. If you scroll up a little where we could see the Z, you wrote Z, the integers, the fields, and then you did the Gaussian integers. And you said, oh yeah, that would make a great test question on knowing what order those would actually come in, even though they're all Euclidean domains. You said that in the video. So I'm wondering, is that the order?
You can point to me what you mean by order. I don't know what that means. I mean, there's no order.
I didn't know what you meant by it either, but I was like, okay, if it can be a test question, let me ask about it.
Yeah, I would have to hear what I said exactly because there's no order in these things. I mean, this is an arbitrary field, right? There's lots and lots of fields, and you know, I guess Z is definitely contained in Zi, right? In the notes, I do a lot of examples with Z square root of -5, right? This turns out not to be a PID, right? So there's something special about I here that's different from, say, square root of -5, right? Where things are different, right? So this is kind of the typical example where you don't have a PID, right? And it's not a Euclidean domain, and lots of bad things happen, right? So in some sense, you want to think Zi is good as a sort of a typical example of good thing, and Z square root of -5 is bad, right? Sort of a typical example of bad thing. Okay, and in the notes, I sort of say why it's bad, right? And I'm going to say something about that in just a second, but okay. But what I've done so far is given you 3 examples of Euclidean domains, okay? We know all Euclidean domains are PIDs. That we know, right? Because we've shown that. PIDs have a lot of nice properties, and so that's what I want to sort of focus on a little bit. So one thing is that in a PID, every prime ideal. I mean, well, I mean, okay. One thing is that these are also have the ascending chain condition, right? But so for any PID, every prime ideal is maximal. So you use that all the time in what you're doing with the field extensions, right? Because when you show that something's prime, you get automatically that it's maximal. And so when you mod out by that, you get a field, right? So you're using that all the time in extension fields, right? So why is this true? So, let R be a PID, a principal ideal domain. Let I be prime. and not the whole ring, right? I don't want it to be the whole ring. I just want it to be a prime ideal that's proper, right? Then our claim is that I is maximal. All right. So to show I is maximal, what do I need to show? I need to show that I can't extend this, right? So I need to show that if I took some A, which is in R minus I, right? I must have that A, the principal ideal generated by A plus I, must in fact be all of R. Right? That would show that this I was actually already maximal because I can't add anything to it and stay proper ideal, right? So I'm going to show that's true, right? Okay, so first of all, I is of the form P for some P, some little p in R. Why is that true? Well, because we're in a principal ideal domain, right? Because we're in a PID, right? R is a PID. So whatever I is a prime ideal. And so it's definitely generated by a single element, right? Because we're in a PID, right? Okay, so suppose, so what is this A plus I? It is really just the same as this 2 generator thing, like that, right? Because I'm really just generating from A and P now, right? When I put those two things together, right? But again, we're in a PID, right? So this has to be equal to some D, like that, right? Let's see, and so in P, I gotta think for a second. Has anyone read my notes? Or let's see, I'm failing to remember what I do next. Let's see, okay, so I'm just gonna think and see if I run and stumble into it. So P is definitely contained in, so I'm assuming that P is contained in D. I mean, that's true because I'm generating, and I'm assuming that this is not all of R. So I'm assuming I have this sort of situation, right? But that tells me then that D must divide P, right? Because remember we talked about this some last time. We have this subset relationship between ideals, right? It gets flipped around in terms of divisibility, right? So if P is in this, it means that P, so it means that P equals, some D times S for something like that, right? Okay, but then what has to happen is that P has to either divide D, right? Or P has to divide S. Right? If P divides D, right, then D is already contained in P, right? Then D is already, right? So I didn't actually make this ideal any bigger when I went up to D, right? So I'm actually getting that those are the same, right? If P doesn't divide D, then this is sorry. Okay, I'm forgetting my own argument here. Let me go find it. You guys get a second break.
Is that saying P divides D or P divides S, or is that what that's saying?
Yeah. Let me find my notes because I'm losing track of my own thoughts here. Oh, it's not this. It's Oh, it's not this, it's this. Okay, sorry.
Further down, we've covered that. There you go.
Is it
Did you
here?
just pass it?
No, this is irreducibility. That's something else.
The product.
Shoot.
Not talking about product.
Let's
That's
see.
ACC.
Oops, let me go. Sorry, okay, hold on. Let me blow this up. So this is an easy argument. My brain's just not getting it at the moment. Oh, wait. I don't want to search everything. I just want to search here. Oh, it's right there. Where is this? Oh, there. It's right there. Right. Okay. You're right. It's right there in front of me. Okay. So let's look at this. Okay. So I say if R is a PID, then every prime ideal is maximal, right? So let this be prime. Suppose it's not maximal, then there's something bigger, right? And so then A equals BC, but A does not divide B by assumption. Because it's strictly bigger, right? A does not divide B, right? So A has to divide C, but then C is equal to AD, because A divides C, and then A equals BAD. Oh, I see. Okay. Okay, so I need something else here. Okay, the reason I'm not getting it is because I need something else from these notes. Okay. So this is also important too. So let me say it and then let's come back to that. Because okay, I forgot that I needed this other little step here. Whoops, that I did not mean to do. Okay, so the last sort of important, there's a lot of stuff in these notes, but the last important thing is this. Usually we call, okay, when you define prime to kids in school, right, you often define primes in two different ways, right? You say P is prime if when P divides A times B, then P divides A, P divides A, or P divides B, right? Another thing we often say, right, is that if, I guess one way to do it is like this. If R divides P, right, then R equals 1 or R equals P, right? So that's sort of a common way of saying when things are prime, right? So another way of writing this would be to say if P equals RS, right? So this is another way of just saying R divides P, right? Then one of R or S, then R or S is a unit, right? And so that's and then the other one is sort of equivalent to RS, modulo a unit, right? So that's kind of equivalent in Z, right? Those are the same. Okay, but in rings in general, that's not true. Okay, so R in a ring is irreducible if and only if, whenever R equals AB, then A or B is a unit. Okay, so this is like this version of saying something's prime. Now the problem in a general ring is you might have lots of other units, right? In Z, you only have 2 units. What are they?
Positive, odd and negative. It's either positive and negative, or is odd and even numbers. I don't know which thing we're talking about.
No, in Z, there's only two units, two things with inverses. What are they? There's only two. Go ahead, Tringle,
Odd
what?
and even.
No, two.
Zero
No,
and one.
not 0 and 1. 0 times nothing is 0 is never a unit.
It's 1 and I.
I is not in Z, but you're getting closer. Okay,
But
1
it's
is one
plus
of
and
them.
minus.
What's the other one?
It's plus and minus 1 and
Plus and minus
or
1.
minus.
Yeah, but minus, those are two, right? Plus and minus 1, right? Those are two
Yeah.
units in Z, right? In ZI, what are the units? This is a good question too, right? In ZI, what are the units?
It's plus
So-
or minus 1 and plus or minus I.
That's right. So there's more units there, right? So there's I and minus I, right? So as you get to more and more complicated rings, you get more and more units, right? Can start popping up, okay?
See, I read my notes.
And
I go through the notes.
and so for A and B in a ring R, let's say in an integral domain, I'm just going to stick to integral domains here. Then you write A is equivalent to B. So this is an equivalence relation. If and only if A and B how do I want to say that? I want to say this. I want to say A equals U times B for some unit U.
I saw that
Okay.
somewhere. I read that somewhere.
So here we say A and B are associates. Okay, so that's the and now, okay, why is this an equivalence relation? I'm going to leave that up to you, right? You want to show that it's symmetric, transitive, all that stuff, right? But here's a good example. If we look at fx, this is sort of our important example, right? These two things would be associates. Right? Because I can factor out this would be the same as 3x squared plus 1, right? But since I'm over a field, this thing has an inverse, right? 3 is a unit, right? So any two polynomials that differ from each other by a constant multiple, right, are associates to each other, right? So those are associates, okay? But more generally, anytime two things disagree by a unit, in terms of, when I say disagree, I mean by multiplication, right? So they're the same up to multiplication by unit, right? They're called associates. Okay, so one way to say that, so S is irreducible if and only if, whenever S equals like RT, right? One of these are units, then this is if and only if S is an associate of R or S is an associate of T, right? So we could go one further and say, you know, S is equal to 1 and R is an associate of T, not R, S. Or, not S, R. So either this is 1 and that's an associate, not 1. Oh gosh. Okay, sorry. If and only if. Okay. R is a unit and T is an associate of S, right? Or the other way around, or T is a unit and R is an associate of S, sorry, T is a unit, R is an associate of S, sorry, S is an associate of R. Okay, yeah. Right, like that. So this is kind of like saying, you know, S is in the integers in Z, right? S is, so what does it say in Z, right? It says S is irreducible if and only if, whenever S is equal to RT, R equals 1 and T, what are the only associates? Or it would be plus or minus S, right? So it could differ by a plus or minus, right? This could be a plus or minus 1. That could be a plus or minus S, right? So basically, you know, something's irreducible in Z if and only if, you know, either when I break it up into a multiple like this, one of these two things is 1 or -1, and the other thing is just plus or minus s, right? So this is sort of what we usually teach kids for one of the definitions of prime, right? And it turns out that in Z, these two things are the same. So in Z, S irreducible, if and only if S is prime. Okay. And this is the kind of thing we need to understand lifted up to these polynomials, right? So it's not always the case. So in Z, square root of -5, right? So in these notes, I do this in this very same area. So I'm just going to kind of point to it if I can see it again. These are principles up here. Nope. Right, so in Z, square root of -5. So here's an example, right? So this has irreducibles that are not prime. So it turns out that 3 is, let's see, let's get it right here. Yeah, 3 is not prime. But is irreducible. Okay, so I would encourage you to look at this example because this is a good example for this kind of thing happening. Okay. So the question is, when are irreducibles and primes the same? Okay, so in Z, they're the same. Okay, it turns out that in Zi, they're the same. In Z square root of 5, and Z square root of -5, they're not the same. So you got to be careful there. This is Z square root of -1, right? So there's a difference between square root of -1 and square root of -5 in terms of its algebraic structure, right? It turns out that in Fx, where this is a field, right, they're actually equivalent, right? So saying that a polynomial is prime and saying it's irreducible turn out to be the same. Okay. And in particular, in a PID, irreducible is the same as prime. Okay, so that covers all these cases up here, right? Because we showed that all those are PIDs. Okay. Now more generally, okay, in a UFD, so this is also a concept you need to understand. Irreducible. Whoops. Irreducible equals prime. So this is a lot like the fundamental theorem of arithmetic, right? It says every number can be uniquely written as a product of primes up to order, right? Okay, so what is a UFD? So as a UFD, if and only if R, well, let's be careful. So for all R in R, there are unique irreducibles. Now you need the notion of irreducible here. This is where it actually becomes important. There's unique, unique irreducibles up to being associates. So that R is equal to the product of these irreducibles. Okay, so what I mean here is I mean that if you have maybe you have R equal to Q1 up to QK, right? And maybe also S1 up to SL, right? where all of these things are irreducible, okay? And what you're going to get then, what do I mean by unique? I mean that K equals L, you actually have the same number. So that's one thing. There may be repetitions, right? There may be repetitions in here. But K is equal to L, and there's some, so once we have K is equal to L, there's some sigma in SK, some permutation, right? Such that QI is an associate of S sigma I. This is just a way of saying I can rearrange these in order to match them up to be associates with each other. Okay. So that's what a UFD is. There's a proof of when you get UFDs here. And at this point in the class, I'm just going to have to let you read it. But I want to say it breaks down to 2 points, and I'm just trying to remember exactly what they are. You need to be so in R, if R is or has the ACC. So this is where this comes up, right? If R has the ACC and between any two elements, GCD of AB exists. So this is called a GCD domain. It could be, and you could use LCM instead. So if those two properties hold, then R is a UFD. Okay. And if you remember back to the beginning of class, one of the exercises was to prove the fundamental theorem of arithmetic, that every number could be decomposed into a product of primes up to order, right? So the order might be different, but the same primes, same number, right? Maybe different order, right? This is the same thing, except here we don't just have plus or minus 1 for our units, right? We have, so we won't say exactly the same primes, but all we can say is up to associates. So that's as good as we can do. We can just say up to associates, right? We have a unique decomposition up to associates, right? Now, how many associates are here depends on how big the set of units are, right? Okay. Okay, and the proof here is exactly like there's an existence part. And there's a uniqueness part. Okay, and if you think back to the proof of that, in the integers, in the existence part, you used induction or minimal member principle or something like that. Okay. Here we're working on an arbitrary ring R. We don't have any sort of induction. We're not in Z, right? But we have ACC, which is giving a finite characteristic to things, right? And so that ACC is what allows us to sort of use something like induction to make this existence part of the proof work. Okay, I know we're all too tired for me to go through that in detail, right? But that's what's happening here, okay? Now the upshot of this is that PID, so PIDs, first of all, satisfy ACC. We showed that earlier, right? PIDs definitely there are GCDs for PID. In fact, this is trivial, right? How did I come up with the GCD in Z, right? Suppose we're in Z. How do I make the GCD from two ideals? How do I make the GCD from that? From two principal ideals. This is where Bezo's theorem sort of pops in, right?
So that's the AS plus equals.
So if I look at the plus here, then this is going to be
equals.
GCD of A and B, right? So if I'm in an arbitrary PID now, right? So this was in Z, say, right? But now if I'm in an arbitrary PID, right? And I have two ideals. I have I and I have J, right? And so what do I know? I'm in a PID. So I know that I is equal to some A, J is equal to some B, right? and I want to show that there's a GCD, right, of this A and B, right? So the claim is just that A plus B, well, this is some ideal, right? It's I plus J, right? So it's some ideal K, right? But because we're in a principal ideal domain, this is some D, right? So it's given like that. And now the claim is that D is equal to the GCD of A and B, right? Now, what does GCD of A and B mean in an arbitrary ring R, right? Well, it should mean that D divides A and D divides B, right? So that should be true, right? Is that true? Is it true that D divides A and D divides B?
Yes.
That's
because
true
it's it's the product of A and B, right?
That's not the product of, but A is clearly contained in D. B is clearly contained in, sorry, D. B is clearly contained in D, right? Okay, but what does this mean when we turn it into division? Is this means the same as that, right? And if I want this to be the greatest common divisor, then what does that mean? It means if I take some other divisor, so let S divide A and S divide B. If this is going to be the greatest common divisor, what do I need to know about S?
If S is going to be the greatest common divisor?
No, D is the greatest common divisor, right? I'm trying to show that this is, I'm trying to show that
S has to be less than D.
It's got to be less than, but in more importantly, it has to divide D, right? It's going to be a divisor, it's going to be smaller, so it's going to divide D, right? So if I take anything here, you know, S dividing A, S dividing B, if I write this in the ideal form, this looks like this, right? S plus B. So when I have division like this, what does this say? All right, remember what, like S divides B corresponds to what? Corresponds to B being a subset of S, right?
Yes.
Okay, so if S divides A and S divides B, right?
Then A is a subset of S.
A is a subset of S, and B is a subset of S, right? So A plus B, right, is a subset of S, right? But A plus B is the smallest subset. This was D, right? So D is a subset of S, right? But this means S divides D, which is what we needed, right? So everything works out beautifully there, right? You know, all the notation, all the orders, everything, you know, works out nice, okay? So in a PID, we have GCDs.
Go back, please. You went back up too fast. Thank you. Thank you.
That's also here, right? And that's the same as this little bit of the notes right here. So the important thing for us mainly is that PID, so first of all, Euclidean domain implies PID, implies UFD, implies that prime equals irreducible, and also that the prime ideal, you know, if this is prime, is maximal. Well, I mean, that doesn't follow from UFD, that follows from PID, right? Okay, so UFD implies that, right? But if I want to add to that any prime ideal is maximal, I need to go back to the PID. That's not true in UFDs, okay? I mean, it can be, but it's not always true. Okay, so the upshot is then in fx, which is where you're doing all your stuff with polynomials, right? So this is a Euclidean domain. All right, so we have unique factorization. That's important. You use that all the time. So you can uniquely factor into products of irreducibles, unique up to unit multiples, right? Okay. So like, you know, over Q, if I have x squared plus 1, that's irreducible. x cubed plus 1 is also irreducible, right? So this now is a product of irreducibles, right? But I could also just multiply this, I could multiply through here by some rational, right? I could look at 3 over 2 x squared plus 3 over 2, right? And 4x cubed plus 4, right? You see, those are really the same up to associates, right? Up to pulling out units. Okay. So I mean, all that stuff you do when you're simplifying things sort of comes up here, right? So pulling out the units, that's like making associates, right? So in particular here, irreducible equals prime, right? So all we need to do is find irreducibles. We don't have to prove things are prime. We just have to find irreducibles, right? And irreducibles are easier to find, right? And so you've got all these theorems about how to find irreducibles, how to tell if a polynomial is irreducible. When a polynomial has degree 2 or 3, how do you tell it's irreducible?
If you can factor it or not, right?
So if you could
factor
factor it, but factoring is sometimes hard. There's an easier way to tell certain things are irreducible. Like over z2x, right, is x cubed plus 2x plus 1. Is that irreducible or not? How do I check without trying to figure out how to factor it?
I already know it's not.
Let me say x instead of 2x.
It's not.
So how do I know that though?
Because the product of A and B well, first of all, there's missing the x squared term. I'm doing algebra in high school. I'm not doing what you want me to do. And I know that we just did one of these problems last week.
Okay, but right now for over Z2, so there's a very specific thing I'm looking for here. If I'm over Z2,
modular arithmetic.
Yeah, but what can I check to tell that something is irreducible? If it's a cubic or a quadratic, what can I check to see if it's irreducible?
I'm looking at AB, right?
Tringle, if you're trying to say something, Tringle's, I see your mouth moving, but you're.
I know. I'm just thinking that like Z2 only has a couple of elements, and we could just check if they are zero, if there's any zeros with those.
Yeah, exactly. You're just going to check to see if there's zeros, right? So, in over fx, right? If I'm looking at f of x of degree 2 or 3, right? If it factors at all, right? So if fx factors, then it's going to factor into some gx rx, perhaps, right? One of these at least have to have degree 1, right? And if it has degree 1, well, it may look like this, right? But I can pull this out and say this is ax plus b over a. I'm in a field, so I can do that, right? But that means that it has to have a root in that field, right? So if I'm looking at degree 2 or 3, and it's not too hard to do, I can just check to see, are there roots there, right? So if you're working over Z2 or Z3 or Z5 or something like that, very often it's just easy to check to see if there's roots.
Oh yes,
right?
Professor, that's like checking the rational roots theorem.
It's kind of, I mean, this isn't exactly related to the rational roots theorem. The one, which one of our theorems is related to the rational roots theorem? So there is one that is related to it. So it says if I have a polynomial fx in zx, and it's irreducible in zx, then what do I know in qx? Is it also irreducible in qx? So in fact, you end up with an if and only if, right? So this is called, does anyone know? I mean, it's in your book. It's in my notes too, but it's in your book. Cauchy's theorem, I think. All right, so f of x is irreducible, assuming f of x is in zx, right, is irreducible over zx, if and only if irreducible over qx. And if you think hard enough about it, this sort of is related to the rational roots theorem. I mean, I'm going to leave it to you to think about that, right? There's a more general version of this that if we have f of x over an integral domain is irreducible if and only if f of x is what is the thing related to q if I just have an integral domain there? So if I want to take an arbitrary integral domain and extend it to a field, right? Can I do that? What's that field called? Is there a unique field that I can extend it to up to isomorphism? This is from, I mean, this was sort of from a few weeks ago, actually, but there's the field of rationals, right? Over an integral domain, right? So if I have an integral domain R, then I can define something we call FR, which is the field of rationals, right? And it's the set of all sort of pairs AB, right? Now, in the end, we would like to abbreviate this like that, right? And so what's going to happen here is B should not be 0 for obvious reasons. And what you're going to have is you're going to have AB is equivalent to CD if and only if. Well, this is supposed to emulate this, right? So so this should be if and only if AD minus BC is equal to 0, right? So you define this relation, and you sort of define, and this is an equivalence relation, and you define A over B to be the equivalence class, right? The set of all CD such that AB is equivalent to CD. All right. And you define addition and subtraction and everything as you would expect, right? So CD equals AD plus BC over BD, right, etc. Okay, so you're just taking an integral domain and extending it to a field. Okay. Some of you teach calculus, all right? Do you do this in calculus class? I know you do. You look at integration and differentiation of rational functions, right? So when you go from Rx, set of polynomials, right, over R, to the set of things that look like f of x, g of x, oops, f of x over g of x, you know, where these two things, sorry, this is the field, right? This is a set of rational functions, right? So something like f of Rx, right? So the field of rationals over Rx would be the set of all fx over gx. Right? So these things we're doing are you use them all the time, sort of without thinking about it too much, right? So I mean, we look at this field of things like this, and we talk about differentiation, integration over those things. You know, a theorem here that's interesting is partial fractions, right? Now we can do partial fractions over an arbitrary field, right? Stuff like that, right? So there's all sorts of stuff that comes up here that you are actually quite familiar with. I mean, this whole section is really about polynomials over fields, which should feel very familiar to you, right? The problem is sort of breaking your old notion of things like prime and irreducible and stuff like that to bring in what you need to make it this new notion, right? You know, so that you have to worry about whether or not you're in a PID and a Euclidean domain and, you know, things like this along the way, right? Anyway, it's 7, and so even just going through that, I never got to the example of how to compute things. So let me point to something, okay? I know I've got a lot of notes I ask you to look at, but I've got a note here about finite fields. It actually has some really important things, like this one, right? So if I have a polynomial over a field that's irreducible, right? And then so when we add a root, right? So when I'm when I have a polynomial and I'm modding out by an irreducible polynomial, right? So now we know that this is a prime ideal because it was irreducible. Irreducible is prime. We know that this is a PID, so this means it's a maximal ideal, right? So this is actually a field, right? And the way we write this field would be F alpha, where alpha really just turns out to be this one thing, this equivalence class. And this acts as a root to this polynomial. So F of alpha equals 0 now in F of X over this. Okay, so we're in that sort of situation, okay? So when we do that, so that's how we add roots. The roots are really just these equivalence classes, right? That's the root we're adding, right? So when we're doing, one way of building complex, over the reals, right, is it's R adjoin I, but it's also Rx modded out by x squared plus 1, right? That's the same sort of thing, right? So the real we're adjoining here is x plus x squared plus 1. That's the thing in here, right? And that's what we're kind of calling I, right? When you look at its algebraic properties, that's that thing there. Okay. The important thing is when I add alpha, if this is an irreducible polynomial, degree f equals some m, right? Then in fact, this thing will split, right? So that's what this proof is here. I mean, for finite fields anyway, right? For finite fields, this polynomial will split over f alpha. So so f of x will split over f alpha. Now this can save you an awful lot of work, because if you try to find the splitting field by hand, it's a lot of work. And you'll see in a lot of my solutions, that's what I do, is I do the splitting field by hand. So I get my one root and then I start doing long division and trying to find other roots, right? And it's a lot of work, right? This isn't so much work. It's still work, but it's not so much work. The other roots here are going to be, so alpha's a root. The field here, f, is a finite field. So f has some size q. I want to use the same notation, right? And so the other roots will be f to the q, or sorry, alpha to the q squared, all the way up to alpha to the q to the, this is the degree, m minus 1, right? So these are the other roots, right? Now when you're doing this, right? So if you're actually trying to figure out what these roots are, right? So this one is actually just x plus fx, right? You know that the part of stuff that goes here should have degree less than the degree of fx. The degree of x, right, which is 1, right? Sorry, whatever goes here, right? And when you're looking at, so an arbitrary thing in fx mod fx looks like gx plus that, right? Where degree of gx is less than the degree of f, right? So like that. So when you're computing these, you can get very large degrees, but you know they should be representable by things with smaller degrees, right? So as you compute them, you want to sort of take a look and say, what is it that I'm actually computing here, right? We're after 7, but if anyone who wants to stay, I'll do one example like this, and so that you can see it, right, sort of in action. Okay. So let's say we take a finite z2 of x. Okay. And is this thing here irreducible over that? So again, what do we have to check? Just, is there a root in there, right? So if I plug in 0, do I get 0? Right, mod 2. If I plug in 1, do I get 0? So there's no root, right? This is irreducible, right? So that thing right there is irreducible. Okay, so Z, if I look at Z2X over this ideal, right? This is going to be isomorphic to some Z. Sorry, yeah, Z2 is a field, right? So that's good. I need a field. Z alpha, well, what is alpha? Well, alpha is just X plus X cubed plus X plus 1. Okay, and what are the elements of this thing look like? Well, they need to be things of degree less than 3, right? So they're going to look like ax squared plus bx plus c, right? Where a, b, and c are in Z2, right? So this is going to be like a 3-dimensional vector space over Z2, right? And so the size of this field is going to be 8, right? And if I want to just describe the elements of that field, I can do it like Z2 of alpha equals, well, I mean, you can define it sort of like we were doing before, right? Like the Zi, like when we added I to R, right? We look like A plus BI, right? So here I could write A alpha squared plus B alpha plus C, right? That's what the field is, right? So once we have that extension, once we have that root, we can just say that's what the field is. Okay. What are the, now I said this split, so in fact the other roots, right? So how would I sort of look for other roots here? Well, I could take x cubed plus x plus 1, right? And I could divide by x minus alpha. I know this is now a root, right? So like, how does that work? Well, you know, I'd multiply by x squared here, right? And I get x cubed minus x squared alpha, right? And I would subtract, right? And so I'd have x squared alpha minus x plus 1. That's what I'm dividing into. Let me call it alpha x squared to make it look more normal. All right, and then so here I'm going to multiply by alpha x. Dang it. All right, so then when I multiply it there, I get alpha x squared. I get minus alpha squared x. Right, so now I'm subtracting off that, right? And so I'm left with here now is alpha squared x plus x plus 1, right? And then I'm going to multiply here by alpha squared, right? So then I get here alpha squared x minus alpha cubed minus alpha cubed, just minus alpha cubed, right? And so now I have here, I should have had some other alpha somewhere. Oh, that's right. Sorry, alpha cubed plus, what am I doing here? Oh no, sorry, I screwed up some x somewhere. Squared x. Oh, sorry, I gotta back up. This right here I did wrong, right? This is alpha squared plus a minus 1x. Right? So where did I do that? That was here, right? So here I need to multiply by plus alpha squared minus 1. Right? So over here I get alpha squared minus 1x, and then minus alpha squared minus 1. Right? And then I'm going to subtract 1, right? So I get here alpha times alpha squared minus 1 plus 1, right? When I'm all done with that, right? That's the remainder now. There's no x anymore, right? Now I'm dividing by a linear. I need to get something with degree 0, right? But this is alpha cubed minus alpha plus 1, right? Which in Z2, which is what I'm working over, is the same as alpha cubed plus alpha plus 1, and that's 0 because that's what we were modding out by, right? So actually the remainder here is 0, right? So after doing all that work, we get here that x cubed plus x plus 1 is actually the same as x minus alpha times this thing up here, right? So x squared plus alpha x plus alpha squared minus 1. Right, and then we're left with this one. We say, can we factor it or not, right? And so now this is a quadratic. You might try to factor it, you have to be careful we're in Z2, so the quadratic formula is going to fail, right? You can't divide by 2, for example, right? So you have to just factor it by hand or do something else, right? Or check, what sort of things do I need to check? What are the objects in this field? Well, they're all things that look like this. So you could, plus C, right? So you could let A, B, and C range over elements of Z2 and just check all those things to see if they're roots, right? But it also turns out, right, that the roots are going to be alpha. Okay, my original field had degree 2, right? So alpha squared, because that's the Q, right? It's alpha Q, and then my degree was M equals 3, right? And so this is alpha Q squared, and that's it, right? So this is alpha Q to the M minus 1, right? So that's it, right? So this is alpha 2 squared, right? So this would be alpha squared, and alpha to the 4, or alpha squared, right? Those would be the objects there, okay? And now you could actually sort of try to figure out what this is, right? So the thing we have is we have alpha cubed plus alpha plus 1 is equal to 0. That's what we have by modding out, right? Alpha squared is just going to be one of these. So alpha and alpha squared are just two of these roots, right? Those are going to each be roots. Now, what is this alpha 4, right? So for that, I got to think a little bit. So alpha 4 is alpha times alpha cubed, right? What is alpha cubed? Alpha cubed is actually minus alpha minus 1. So this is alpha times minus alpha minus 1. All right, so this would be minus alpha squared minus alpha. Right, and so the three roots I would get here would be alpha squared, and that thing, right? Because all of them should have this form like that. They should all look like A alpha squared plus B alpha plus C. Okay, so you can't just directly use this result here. You have to do a little computation, but this can save you a lot of work. Okay, so that's the upshot. So I mean, first of all, you know ahead of time that the field that the polynomial will split. So you don't have to try to prove that it splits or not. You know ahead of time that it will split. And you even know what the roots are, but you have to do a little bit of work to get the roots in the right format. Okay, so that's an important theorem here to use. This one's also important that you've used. Sometimes you can just read it. But anyway, this one's one you might want to use for actually doing problems, right? That's all I'm going to say. Any last minute questions or? Okay. All right. See you later. Bye-bye.
Thank you.